Hello everyone. Okay, we are looking at topic 8.3, weak acids and base equilibria. It's on page 14. Okay. And if you watch another video on this, or you watch a video that they post like on College Board, they make it very complicated, but we really can simplify this down, and that's what I'm wanting us to do. One thing that's really important is recognizing relationships between values. Like, there's so many questions that you don't have to calculate if you just know the relationship behind these things. So we've talked about this before. If we have a larger amount, if we have a higher amount of H plus, this would make our item a stronger acid, okay? And so stronger acids have lower pHs. Okay, now K values, we're gonna get to a unit where we're gonna discuss what these K values are in more detail. But right now, I just want you to recognize that they are directly proportional to concentration. So if we have a larger amount of H+, if we increase in our H+, then we increase in our Ka, our equilibrium constant, K, for acids. So the higher the concentration of H+, the higher the Ka value is. But just like with pH, remember how P means negative log? Like, just a reminder that P, this means that we take the negative log. Gosh, the negative log of something. So in this case, when we did the pH, it was the negative log of H, or H+. And if we have pKa, then we do the negative log of Ka. But a p-value compared to what you're taking the negative log of is always inversely proportional. So if we are increasing in H+, then we're going to decrease in pH. And if we're increasing in Ka, then that means that we're decreasing in pKa. So keep these things in mind, right? Like, an acid is stronger when it has more H+, when it has a lower pH, when it has a higher Ka, or a lower pKa. And then we can do the same thing for bases. And you can flip all of those arrows, right? Like, it's completely appropriate to say, well, the lower my H+, the higher my pH will be. The lower my Ka, my equilibrium constant for acid, will be, and the higher my pKa. Okay, those are our acids. Now we can do the same thing for bases. We could say, hey, the larger, the greater amount of OH minus that I have, the stronger of a base it is, which would decrease the POH, which would increase the Kb, the equilibrium constant for a base, which decreases the pKb. Oh my goodness, as I write A. And I know that these questions try to trick you. They'll give you like a pKb instead of a Kb, so you need to know these relationships. So again, what if it was a weaker base? Well, then we would have less of this OH minus. Its POH would be higher. Its Kb, equilibrium constant, would be lower. And you would have a greater pKb. So these K values and the concentrations are directly proportional. When one goes up, the other one goes up. And the P values, compared to their original item that we're taking the negative log of, they're always opposite. They're inversely proportional. And those two are inversely proportional. All right, great. So if we look at this practice problem, it says, which particle drawing best represents a portion of sample 1? Note that water molecules are omitted. So if we look at sample 1, is really similar, like the concentration is the same for the other samples, but it definitely has a lower pH. Well, a lower pH would mean that it's got a higher concentration of H+. But don't forget, anytime we have H+, we could replace it with H3O+. And guess what? I see 3 hydrogens and 1 oxygen. So I would say that's an H3O+. So if this is a lower pH, then there's a lot more of those floating around. So I would think that it's probably B, because there's more of the H3O+ in that solution. This equation and this equation, they are on your blue reference, or sorry, blue reference, your green reference. So if you look on the back there where it says equilibrium, so here it tells us, look, remember I told you how the p-value is just the negative log of this, so pKa is just the negative log of Ka, and pKb is just the negative log of Kb. And then here's the 2 equations just above that. There's the Ka and there's the Kb. Okay. Now it looks a little funny because it's like, what is this H3O+? Oh, well, we could just replace that with H+, if that's helpful. But then what is this A-, and what is this HA? Okay, let me explain. If we have a weak acid that, and it's interacting with water, it doesn't even need to be interacting with water. Like, I'm going to rewrite this. So this NH4+, okay? Well, we know that if it's an acid, it wants to lose an H+. So what if we lose that H+? That would leave us with NH3, because we lose a hydrogen, and we also lost that plus, so it would just be neutral, like that. See the NH3? Great. This was our weak acid, our thing that had the hydrogen, something that had an extra hydrogen on it. And then we lose that extra hydrogen. See, there's the H+, there's the hydrogen. And what we are left over with is this A without the H+. So it's the A without that H+. So the weak acid, or the acid, is the HA, and the A-, this is the conjugate base, and then we have our H+. So we have our H+, we have our conjugate base, and we have our acid. I want you to notice something important though. And the first thing is that if I have one of these that breaks apart, like there's probably a ton of these in there, but if I have one of these that breaks apart, it will always make one of those and one of those. So no matter how many of these break apart, the amount of H+ and the amount of NH3 will always equal each other. These will always equal each other. And they're in the same solution, they're in the same volume. So if H+ always equals NH3, then the concentration of H+ always equals the concentration of NH3. Or let's use this symbols here. For any acid, but certainly a weak acid, the amount of H+ will always equal the amount or the concentration of the conjugate base. Those things will always equal each other. Okay, great. So what's cool is that you can rewrite this equation if that's the case. Like, if H plus equals A minus, then this thing that we started off where Ka is equal to H plus multiplied by A minus divided by HA. Couldn't we change that? Couldn't we, what if we call the concentration of H plus and the concentration of A minus? What if we just, as a placeholder, we replace it with X? So this would mean that Ka would equal X times by X divided by the concentration of HA, right? Well, X times by X, isn't that just X squared? So Ka is equal to X squared divided by HA. What's crazy is that these problems with these weak acids, they want you to solve for the pH. And remember how pH is just the negative log of H plus? So if we can solve for X, if we can figure out what H plus is, then we can just take the negative log of that, and that will be the pH. So this, let's rearrange it to solve for X or H plus, right? So I'm going to multiply my concentration of the acid. So HA times by Ka, this equals X squared. But then if I want to isolate X, then I take the square root. So the square root of those things multiplied together equals X, which is the concentration of H plus. Every single time I've seen one of these problems, they give you the concentration of the acid, they give you the Ka, and they ask for you to solve for the pH. So if it's a free response, then justify your answer by showing them this. Say, hey, this is true, and if I take the square root, if I rearrange and solve for X by taking the square root, that will be the concentration of H plus, which I can then plug into my pH equation. I know, you're doing great. This is actually a far simplified version of what most videos show of this. It just takes practice more than anything. We're going to come back to KB here in a second. I think I would rather, okay, turn the page to page 16. And see how you have practice problem 16 and practice problem 17? Look at 17. The pH, so we're solving for pH. We're trying to find pH. pH of a 0.01 molar HNO2, not HNO3, HNO2. So this is a weak acid, okay? So this concentration of HNO2, or if it helps our brain, we can just call this hydrogen with something else attached to it, right? The HA. This weak acid is 0.01 molarity. That's the concentration. The pH of the 0.01 molar HNO2 solution is in which of the following ranges? And so we're solving for pH. For HNO2, the Ka, so our Ka value is 4 times by 10 to the negative 4. All right. If this is a free response, this is what they would need to see. So the first thing is you would need to say that the concentration of H plus is equal to the concentration of A minus. Like, we just had to justify, we have to show the graders that we know this, that they're always going to equal each other. And if it's helpful for your brain, because it is for mine, I'm going to replace it with x in the equation. And the equation that's given to us on our reference is Ka is equal to H plus A minus over HA. H plus, the conjugate base, and the concentration of the acid. But I just, up here, I said these equal each other, so I could say x squared over the concentration of the acid. Now let's rearrange and solve for x. So if I take the concentration of the acid and I multiply this by Ka, that will equal x squared. But then if we take the square root of both sides, then that just equals x, which is H plus. All right, great. So the acid had a concentration, the weak acid had a concentration of 0.01. And I'm going to times that by Ka. And Ka was 4 times by 10 to the negative 4. Okay, that's when we multiply those answers, that's what we get. Those values, that's what we get. But we need to take the square root of that. So then the square root of this. Okay, so my concentration of H plus is 0.002 molarity. All right, great. And my final step to getting my pH, because I know what H plus is, so pH is the negative log of H plus, or 0.002, and the negative log of 0.002 is 2, let's see that concentration, 2.7. So that would mean my pH is in between 2 and 3. All right, nice. I only go through this process where we take this equation and we say that they're equal to each other and solve for x. Like, only go through this process to get pH when it's a weak acid or a weak base. But the good news is, guess what? Weak acids and weak bases, the process is incredibly similar. So look at this. Here's a weak base. And I can tell that it's a base because it's going to gain a hydrogen. So this is our conjugate acid. And then water acts like an acid. This is our conjugate base. Okay. So similar, this is our base, and we're going to replace that with just the symbol B for now. Okay. And then, yeah, we got water. And when a base is going to take a hydrogen, but where it takes a hydrogen from is a water molecule. So that would leave OH minus behind. And then the base that we had before gained a hydrogen. So it's like we had the base, but it gained an H plus. Yeah, similar to acids, like I told you. See how for every one hydroxide, there's one NH4? No matter how many water molecules break apart and bases steal those H values from the water, no matter how many of that reaction occurs, the hydroxide always equals the conjugate acid, always. So it is completely appropriate to say that for a weak base, the amount or the concentration of OH minus will always equal the concentration of the conjugate acid. That will always be the case. And if these things always equal each other, well, then we can rearrange, we can change this equation. Just as a placeholder, how about we call both of these things, because they equal each other, how about they're x? So similar to like what we did before. This becomes x, and this becomes x. But x times by x is just x squared, right? So Kb will equal x squared over the concentration of the base. So if we solve for x, we'd multiply the concentration of the base times by Kb. That would equal x squared. So if we take the square root of both sides, then the concentration of the base times by Kb, and then take the square root of that, that equals x, which is your concentration of hydroxide. So in order to get POH, you would just take negative log of whatever that x value was, whatever that concentration of hydroxide is. That would be POH. All right, great. Let's just one more time together. On practice problem 16. So, caffeine is a weak base. We go, great, because I couldn't tell from just that. So I couldn't tell from just this that it's a weak base. With a Kb value, okay, so Kb is equal to 4 times by 10 to the negative 4. We're solving for pH. The pH of the 0.01 molar, so that means this is the concentration, solution of caffeine. So this caffeine, this base, concentration of the base was 0.01. And we're trying to figure out pH. All right, so because this is a base, we can say that the items in the numerator, the hydroxide and the conjugate acid, these equal each other. Same thing, if it was an acid, we say the items in the numerator equal each other. So the concentration of hydroxide equals the concentration of Hb+, which we're going to replace with x. So since we've replaced that with x, we can say Kb is equal to x squared over the concentration of this base. And we can rearrange and we can solve for x. So if we take the square root of the concentration of the base times by Kb, that equals x, which is the amount or the concentration of hydroxide. All right, let's plug that in my calculator. So the base was 0.01. That's the concentration. The Kb was 4 times by 10 to the negative 4. So there's those items multiplied together, and then I take the square root of that. So hydroxide has a concentration of 0.002. That sounds familiar. But this is not the concentration of H+, it's the concentration of OH minus, hydroxide. So if I take the negative log of that, it's not pH, it's POH, right? POH is equal to the negative log of 0.002, which we know is equal to 2.698, etc. Okay, that's the POH. And so then the final step to get pH, we know that if we do 14 minus POH, that will give us our pH. So 14 minus the POH, our answer is 11.3. Okay, great. And so that means that our pH is in a range between 11 and 12. All right, so when you are calculating pH or POH of a weak acid or a weak base, we need to use the the weak acid or the weak base equation, right? So like Ka is equal to H plus A minus over HA, or if it's a base, Kb is equal to hydroxide, our conjugate acid over our base. And then set the two items in the numerator equal to each other, right? So make sure you tell them that H plus is equal to A minus, or that OH minus is equal to HB plus. And then rewrite the equation. So we have Ka is equal to x squared. Oh yeah, let's just throw, like, we're gonna call those x. X squared divided by the concentration of the acid, or x squared divided by Kb, the concentration of the base. And we're going to solve for x. And then the last step would be taking the negative log. Then take the negative log of that x value, and that will give you the pH or the pOH. Okay, we're just going to get lots of practice doing this in class. See you all soon.